Hello, and welcome to the lecture on Chapter 5 of Astronomy Today. This chapter is all about telescopes. We're going to learn a few details about telescopes and some interesting facts about all the ways that astronomers use, well, telescopes. Okay, so here's an example of a telescope with a large mirror that you might see up in a high mountain location on Earth. Okay, all right, so let's take a look at our sections that we're going to cover. We're going to talk about optical telescopes. Those are ones that use visible light. We'll talk about the importance of telescope size, including a formula to relate something called angular resolution to the size of the telescope. We'll talk about images and detectors, high-resolution astronomy, radio astronomy, so that's not using visible light, interferometry, space-based astronomy, that's having telescopes that are in orbit around Earth or somewhere else, the ALMA array, and full spectrum coverage. So other types of electromagnetic radiation besides radio and visible. All right, so let's talk about optical telescopes. Okay, so optical telescopes, well, at least one type of them, uses the property of refraction. Now, refraction is the concept that light bends when it moves from one medium to another. So for example, if light is moving from air to glass, well, light travels at different speeds in air and glass. Now I know that the speed of light is a universal, but that's the speed of light in a vacuum. When light is traveling through a material, it slows down. For example, when it's traveling through glass. And as light is traveling through that transparent material glass, the slower speed results in a bending of the light, as shown here with the bent path. That process is called refracting, or the refraction of light, okay? And we see that there are refraction angles due to different shaped prisms. And because of that, we can have light refracted through a lens so that all the light focuses on a single point. All right, the detector, you can think of a digital detector in terms of a digital camera, or perhaps just the eyepiece where the observer is looking, okay? But the idea there is that the different curvatures of the lens, here simplified as different rectangles and trapezoids and triangles, but the different curvatures of these lenses can allow the light to all get focused at a similar point, okay? So that's the refractive focusing of light. Now, light can also be collected through reflection. The idea here is you can have a curved mirror. The different curvature points allow for light to get, again, focused on a single point, but here done through reflection. The principle there is that the angle of incidence for reflection is equal to the angle of outgoing light. So in this case, theta with an I is equal to theta with an F. Those angles are always equal. So if light comes in at a steeper angle, then it leaves at a steeper angle. If it comes in at a less steep angle, then, well, you get it, it leaves at a less steep angle. So that's the very idea of focusing with reflection. So far we've talked about focusing with refraction and reflection. Reflection uses mirrors, refraction uses lenses. And that's really so much of what telescopes are about, either the use of lenses or mirrors, or both, okay? So reflecting and refracting telescopes. So here's an example of a refraction telescope. These tend to be long telescopes. They have a single lens or multiple lenses, and then they have a focus point and an eyepiece, which always includes its own lens. Then we have a mirror that involves reflection, shown here, with a single mirror, a primary mirror, which is the curved one, another mirror, which is the secondary mirror, kind of acting like just a tool to redirect the light, okay? And so that's what the secondary mirror is used for, because there's a focus right here. But that focus really isn't used. Instead, the light is interrupted or intercepted and then redirected to an eyepiece. That's the typical way that it's set, that this type of telescope, a reflecting telescope, would be set up, okay? So modern telescopes are all reflectors, okay? The major ones are all reflectors. Light traveling through a lens is refracted differently depending on the wavelength. Some light traveling through lenses is absorbed, and large lenses can be very heavy and can only be supported at the edge. Right? There's no way to have a support in the middle because that would interfere with the light. A lens needs two optically acceptable surfaces. Mirrors need only one, okay? So notice that, right? You just need that single primary mirror. Here you have to make sure that this surface is of high quality and so is this surface. Where in the case of the mirror, you only have to check for that high quality that single surface, you can have a rough, not very carefully manufactured surface on the other side. So the point here is that all modern telescopes are reflectors, but those are just major modern telescopes, because hobby telescopes, or even just people that want to use telescopes at home, definitely can use refracting telescopes, ones that look like this. Okay, so here are types of reflecting telescopes. Okay, so we have those that have a prime focus, a Newtonian focus, a Cassegrain focus, and a Nasmyth focus. Okay, and you can see it's all about having different orientations of mirrors. All right, so to have a prime focus, the observer would have to be here. All right, so you'd have to say put the lens at that location. That can be very difficult because it's interrupting the actual oncoming light from the sky. So most cases like this are going to have a Newtonian focus to intercept the light and redirect it to an eyepiece that's mounted on the outside of the telescope, right? Hobby telescope or not. But you can see you can have other cases where the light is passed right back through an actual hole in the primary mirror, or you can have a case where you just add another mirror so that you can have a lower eyepiece, okay, closer to the primary mirror. So the Keck telescope is a modern research telescope. It's a great example of that. We can see that it has incoming light. We have a very large mirror down here. This is the primary mirror. Then the light is reflected onto the secondary mirror, and then a tertiary mirror, and then finally the Nasmyth focus. So it was the fourth type. Okay. All right. So the Hubble Space Telescope has a variety of detectors. Okay, it's including those that use mirrors. All right, we can see an example of the primary mirror. Okay, and the Hubble Space Telescope's main mirror is 2.4 meters, so about 8 feet in diameter, and is designed for visible, infrared, and ultraviolet radiation. And here we compare the best ground-based image of a particular galaxy, the M101 galaxy, with a Hubble image of the same. And we can see that the Hubble image is just inherently higher quality. It's a much crisper image. Why? Because the Hubble telescope is in space, and being in space has huge benefits for the use of light telescopes. Okay, so as far as telescope size is where I want to introduce one of the key ideas in terms of the quantitative tools we can do in the class involving telescopes. Well, let's discuss this. Light gathering power improves the detail. Okay, brightness is proportional to the square of radius of the mirror. Okay, so in other words, if you want to talk about how much light is coming in, then you would say that the brightness is proportional to the square of the radius, so r squared. So if I have a telescope that is twice as big as another telescope, it will resolve an image that is 4 times as bright, because 2 squared equals 4. If I have a telescope that has a radius that is 3 times as big, then how much more bright will the image be? Well, it'd be 3 squared, so 9 times as bright. So it's a squared relationship. Okay. Now, if you just have another telescope and you combine them together, then you would just double. But if you increase the size, then the brightness of the image goes up with the square of the radius. Okay. So as far as resolving power, all right, well, resolving power is better, or when better, you can distinguish objects that are closer together. Okay, so instead of them being a single blurry object, we recognize they're 2 distinct objects. So this is the very process of resolving power. Okay, you go from not being able to tell if they're 2 distinct objects to clearly seeing that we have 2 distinct objects side by side. And since we're using telescopes at the very limit of their ability, we often are doing just this, discerning 2 blurry objects next to each other. So resolution is proportional to the wavelength and inversely proportional to the telescope size. So bigger is better. Okay, the formula is the following. Okay, so angular resolution. Okay, and this is in your textbook as well. Okay, which is in arc seconds. Right, so arc seconds is equal to 0.25. This is like a fitting number times the wavelength in micrometers divided by the diameter in meters. Okay. D for diameter, lambda for wavelength. Okay, lambda just represents the wavelength of light, D the diameter. So we see that indeed making the telescope bigger is going to make the angular resolution smaller. That means we can resolve smaller things. We want the angular resolution to be as small as possible. because that's telling us that we have, if this is only a tenth of an arc second, say 0.1 arc seconds, right, a tenth of an arc second, then we're not able to resolve something that small if our diameter is too big. Because if we're dividing by a big number here, okay, or rather it's too small, excuse me, if we're dividing by too small of a diameter, say only 1 meter, then our angular resolution is going to be big, which means we're not actually able to resolve the small things. So again, we want this to be small is good for angular resolution, which means diameter is big or should be big. Okay, so small is good for angular resolution. Okay, hopefully that idea makes sense. You want angular resolution to be small, thus you want the diameter of the telescope to be large. Makes sense, okay? Now what about wavelength? Well, the importance of wavelength here is that inherently you have larger angular resolution when your wavelength is larger. So having a shorter wavelength means it is easier to discern objects that are closer together in their actual separation in the sky. All right. So looking at shorter wavelength light allows for finer angular resolution, smaller, better angular resolution. Very large wavelength is inherently a little bit harder to work with in terms of high resolution. Okay. All right, so here is the effects of improving resolution. All right, so here we have a 10 arc minute, 1 arc minute, 5 arc seconds, and 1 arc second. So you can see that as our resolution gets smaller, the image gets much crisper. Okay, because that's the idea. Now we're in the last case, in case D, we're distinguishing between dots that are only 1 arc second apart. So that's basically each pixel is only 1 arc second, so you get a really nice image. Okay. So as far as image acquisition, charge coupled devices called CCDs are electronic devices which can be quickly read out and reset. So this is the idea of a digital camera, okay? All right, so image processing by computers can further sharpen images. So there's a lot of filtering in terms of like filtering out noise and distinguishing what is the true signal. So there's a lot of kind of after analysis that's done with these images that are picked up by computers. So it doesn't just come down to the actual manufacturing of the quality of the mirrors or the size of the mirror. Using computation power is important, but neither on its own is enough, right? You have to combine computation power with large, very finely made telescopes. Okay, so what about high resolution astronomy? Where we've kind of been, hinting at this idea about how do we make telescopes as good as possible? One thing is to acknowledge that we have atmospheric blurring, and it's due to air movement. Because if a signal is coming in, if a signal being light, electromagnetic radiation, is passing through the atmosphere, then that signal is getting bounced around, and inherently it's vibrating. Okay, and that vibration is important when we're trying to distinguish things that are a fraction of arc second apart. All right, so what are the solutions to that atmospheric interference? Well, put telescopes on mountaintops, because the air is much thinner and simply the light signal, is passing through less of the air, okay? But even better than mountaintops are space, okay? Putting telescopes in space. The Hubble Space Telescope was the first, but there have been many space telescopes since, including one that's going to be launched in the next year or so called the James Webb Space Telescope. And it's just a testament to how far we've come. And space telescopes are starting to replace ground telescopes, but we'll probably never replace them completely, okay? All right, so active optics is control mirrors based on temperature and orientation, right? So really to acknowledge the variations in the system and counteract them, even tiny vibrations, okay? So here we have a track of atmospheric changes with a laser and then adjust the mirrors simultaneously. And obviously this has become more possible for this type of real-time adjustment based on incoming data like that collected through a laser reflecting off the atmosphere due to the quick and powerful computation power that is combined with these telescopes. Okay, so these images show the improvements made possible with adaptive optics. Okay, so here we have one without and with. And here with adaptive optics, we can clearly see two sources of light, such as in a binary star system, with only a 1 arc second separation in terms of how they appear in the celestial sphere, which is something we couldn't not distinguish without adaptive optics, because here it's just a single blur, and we can't be sure that it's actually two separate stars, or perhaps a star and a planet even at the extreme end of imaging. Okay, so what about radio astronomy? Because we've been talking a lot about light and the use of mirrors, but certainly astronomers don't just look for electromagnetic radiation in the visible spectrum, they look at radio waves too. So it's similar to optical reflecting telescopes. They have a prime focus, but in this case, it's using radio wave. radio waves. They're less sensitive to imperfections due to the much longer wavelength and can be made very large. Because the idea is that we've been talking about, in terms of optical telescopes, we've been talking about wavelengths on the order of 1 micrometer, and usually more like half a micrometer. Because you think about visible light, often 500 nanometers, a nanometer is half a micrometer, okay, or 500 nanometers is half a micrometer. On the other hand, when we're talking about radio telescopes, we're talking about, so this would be optical. When we're talking about radio telescopes and their wavelengths, we're talking about wavelengths that are on the order of a meter to even 10 meters. So these are much, much longer electromagnetic waves, which means we can have very large telescopes, okay, that don't look anything like telescopes because they are in fact radio dishes, but they're still working on the same principle of having incoming radiation getting reflected off a surface and then focused, okay? But they're made on a much larger scale and they're inherently less precise because the waves are so much longer. All right, here's an example of the largest radio telescope in the world that recently collapsed. This was in the news a couple months ago. This whole thing fell down and now this telescope is no more. As you know, on Earth, we have lost our largest radio telescope. It is irreplaceable and we don't have anything currently to replace it. But of course, scientists and engineers will address that and in the future build something comparable. But for now, this telescope no longer exists, sadly. Of course, these slides are not up to date. Okay, all right, so continuing with radio astronomy. The longer wavelength means poor angular resolution. It's just part of dealing with radio astronomy. Now, that said, that doesn't mean radio astronomy is inferior in any way to optical astronomy. There are many signals that come from especially deep space that only exist in the radio spectrum, or even signals that come from the center of our own galaxy that only exist in the radio spectrum. So we must take advantage of that part of the electromagnetic spectrum, but we have to acknowledge its limitations. Okay, the advantages of radio astronomy is we can observe 24 hours a day because radio waves are not washed out by sunlight. Clouds, rain, and snow do not interfere at all because those wavelengths are so much longer than the actual size of, say, rain droplets or snow or any molecules in the air. And observations are at an entirely different frequency, so we get very different information. All right, so interferometry, what is that? Well, it combines information from several widely spaced radio telescopes as if it came from a single dish. The resolution will be that of the dish's whole diameter, the largest separation between dishes. So in this case, this group of dishes, this array, right, this array of dishes works like a single large telescope. So it has a size that's much larger than a single telescope. And that's something that is unique to radio astronomy. We cannot do this with optical light because of the high precision, but here we can collect that data and we're effectively building one giant radio telescope out of many smaller ones. So interferometry involves combining signals from two receivers. The amount of interference depends on the direction of the signal. All right, so notice the idea of the interfering waves. That interference comes up in the name of interferometry. So obviously when scientists and engineers build arrays like this, they carefully know the distances between every telescope so they can calculate that interference and thus collect their data. Okay, so we can get radio images whose resolution is close to optical, and interferometry can also be done with visible light, but is much more difficult due to those shorter wavelengths. Okay, so it's not done on such a large scale by any means. Okay, so space-based astronomy, where I mentioned a couple times that it's kind of the future of astronomy. So what's it all about? So one idea is infrared radiation can produce an image where visible radiation is blocked and generally can use optical telescopes, mirrors, and lenses. All right, so infrared telescopes can also be in space. This pair of images compares the Eagle Nebula in infrared taken by the Herschel Space Observatory with the same region in the visible light. Okay, so notice the observation in visible light and the observation in radio waves. We can see a lot more going on in the radio waves in this region that is artificially colored as red because this is light that would normally be blocked by interstellar gas and just appear as black. Okay, it's basically the black spots between the stars. But here, instead, we have the stars still showing up as bright spots, like the red dots that I'm drawing. But in between, we see all these shades of artificially colored red representing those infrared waves. The Spitzer Space Telescope, an infrared telescope, is in orbit around the sun. These are some of their images. Okay, so these are space-based images of infrared spectrum, right, shown here. The ALMA array is a set of 66 radio telescopes located in northern Chile, which detect radiation with wavelengths between 0.3 millimeters to 10 millimeters. This is really kind of in the microwave section of the electromagnetic spectrum, all right? And then this huge array allows for excellent resolution, right? And the fact that it's high up on a mountain means that there's less atmospheric interference, although that's not that important for radio waves. At such a high precision, it is relevant. There's also ultraviolet. Now, ultraviolet is interesting because it has to be done in space, okay? So infrared observations can be done on Earth, right? We can take infrared images of distant galaxies or even things within our own solar system, but we can't use any signals that come to Earth via ultraviolet because our atmosphere completely absorbs ultraviolet radiation, okay? Well, at least very nearly completely. So it must be done in space, okay? And that means that all ultraviolet telescopes are space-based. And here is a result of one of those ultraviolet telescopes. All right. X-rays are another example of a type of electromagnetic radiation, very, very short wavelength, high energy electromagnetic radiation that doesn't really reach Earth's surface at all. It gets completely absorbed in the upper atmosphere. So again, we have to observe it in space. Okay. And the very, very short wavelength requires these very sophisticated nested cylindrical mirrors in order to focus the actual X-rays on a single point. And that's because the wavelengths are so much shorter than visible light. So unlike with radio waves, where we have some flexibility on how to build telescopes, including an array of dishes like this, we have almost no flexibility when we're trying to observe X-rays. And instead, engineers have to be very ingenious and genius about how they closely pack together lenses in order to actually get a reasonable focused image. All right, so here is the result of all that hard work. Here's an X-ray image of a supernova remnant showing the signal that gets transmitted and then received by Earth in X-ray because it's such high energy. In this case, the X-rays are being produced by incredibly fast-moving electrons, moving in an appreciable fraction of the speed of light, rushing away from a supernova. Okay, there's also gamma rays. Gamma rays are essentially high-power X-rays, but they're the most high-powered type of electromagnetic radiation out there, right? And they cannot be focused at all, and therefore the images are very coarse. Okay, now might we discover a way to focus them with some sort of nanotechnology of building mirrors at a nanoscale? Quite possibly, but we're just not there because mini gamma rays are 10 or 100 times shorter than the typical X-ray. All right, so much can be learned from observing the same astronomical object at many wavelengths. Here are examples of the Milky Way, right? Observing it in the optical spectrum. Here we have the optical spectrum down here. All right, observing it in the ultraviolet. All right, observing it in the X-ray, and then even observing it in the gamma ray. All right, so I'm making all these different observations. We can see different things that are going on, different parts of the phenomenon of the cycle of star death and birth that occurs in something on the scale of a whole galaxy. So in summary, refracting telescopes make images with lenses. Those are fine for hobby telescopes and small telescopes. All major scientific telescopes are reflecting telescopes that use mirrors. Modern research telescopes are all reflectors. CCDs are essentially digital camera sensors. Data can be formed into images, analyzed spectroscopically, right, and calculated and filtered with computers. Large telescopes gather much more light, allowing the study of very faint sources. We saw the relationship between size and brightness, right? That's the gathering of light, and it's a square relationship. So you double the size of a telescope, you get 4 times as bright an image. Large telescopes also have better resolution. We also saw the formula for that, which showed that there's a direct inverse proportionality between the size of the telescope and the angular resolution, okay? You don't have to square it in that case, in other words. Resolution of ground-based optical telescopes is limited by the atmosphere. Resolution of radio or space-based telescopes is limited by diffraction. That's always kind of the limiting case. Active and adaptive optics can minimize atmospheric effects. Radio telescopes need large collecting areas, and they're also diffraction limited. Interferometry can greatly improve resolution. Infrared and ultraviolet telescopes are similar to optical. They basically work on the same principles, but often they're in space, okay? Especially ultraviolet, all right? And they must be above the atmosphere in the case of ultraviolet. X-rays can be focused, but very differently than visible light, and gamma rays cannot be focused at all. Thus, they always create coarse or grainy images. Okay, all right, so I hope this chapter all about telescopes has been interesting and informative. Thank you so much for watching the video.